So welcome back to our last part of lecture 4. So in this particular lecture, we're going to be looking at heteronuclear diatomics. So up to this point, the molecules we've been looking at have been homonuclear diatomics, where the atoms are the same on both sides. For heteronuclear diatomics, we're going to have different atoms on the two sides of a molecular orbital diagram. This is a more complex situation than homonuclear diatomics, mainly because your orbitals on the two atoms are going to be different, and that can cause some different situations. What causes those energies to be different is the dependency of orbital energies on the Z effective. So remember, your Z effective is the total nuclear charge that an electron in an orbital feels due to the positive charge from the nucleus. And we have shielding and penetration affecting both of those things. As a general rule, as you go farther right on the periodic table within a period, your Z effective is going to increase and your orbital energies are going to drop. So the greater the Z effective, the lower the orbital energy. If you're just looking at two atoms and you're not quite sure where they're at, you can always take a look at the electronegativity of the two atoms. It's a good gauge of orbital energy. It's also affected by Z effective, which is why those two things follow the same trend. So the more electronegative an atom is, the lower in energy the orbitals are going to be. The interactions are varied when you have heteronuclear diatomics because you have different types of orbitals at different levels for different atoms. And if they come from different periods, that can really cause things to be really varied. What you always have to look at is the energy of the orbitals. They need to be fairly similar, and the symmetry of the orbitals has to be taken into account. We'll look a lot more at symmetry of orbitals in the next lecture, next week's lecture. Let's take a look at the orbital interactions. So when bonding atoms are the same, so in a homonuclear diatomic, the orbital contribution from each atom in a bond is the same. Sorry for the typo there. When the atoms are different, then the contributions to a molecular orbital are generally different. So if you have two orbitals interacting, again, they're going to have a lower energy orbital for bonding and a higher energy orbital for anti-bonding. The lower energy atomic orbital will make a greater contribution to the bonding molecular orbital because it's closer in energy to that molecular orbital. And the higher energy atomic orbital will make a greater contribution to the anti-bonding molecular orbital. And we'll see an example of that here in a moment. Now, the other thing that can happen is you can have orbitals on one atom that don't have a good match in terms of either symmetry or energy, or both. And they won't form a bond of any sort with any other orbital on the other atom. And so those end up as non-bonding orbitals. So these occupy the molecular orbital diagram as lone pairs. And as you saw, hopefully in the previous course that we did, your MO diagram or your MO diagrams are going to give you the same number of bonds, same number of lone pairs as you would have in a very simple Lewis dot diagram. So if you have lone pairs in a dot diagram, then you should also have some lone pairs in your molecular orbital diagram. So let's take a look at some heteronuclear molecular orbital diagrams. Here we have a very simple one. We have NO. So N and O, nitrogen and oxygen, are right next to each other on the periodic table. So their energies are very close to each other. So this looks like a pretty normal molecular orbital diagram that we've dealt with before in the homonuclear molecules. What we see is we've got the 2s here, a little bit higher in energy than the oxygen. The oxygen is a heavier atom. It has a higher Z effective. It has more protons than the nitrogen. So its energies are just slightly lower for the 2s and the 2p. Notice we still have sigma 2s, sigma 2s star, sigma 2p, sigma or pi 2p. And what we could infer a little bit from this diagram is that if we were to look at a calculation of the molecular orbital makeup of like the sigma 2s, it would have a little bit more of the oxygen 2s contribution than the nitrogen 2s contribution because it's closer in energy to the sigma 2s. And for the anti-bonding, the antibonding would have a little bit more nitrogen character than oxygen character. Same would be true for the sigma 2p, a little bit more oxygen character than nitrogen character. Same for the pi 2p, they would all be a little bit more oxygen heavy. And then these anti-bonding orbitals here would be a little bit more nitrogen heavy. Now, if we go to something like this where we have hydrogen fluoride, hydrogen and fluorine are far different in energies. You have the hydrogen, which is a group one, or a period 1 element, fluorine, which is a period 2 element, and all the way on the other side of the periodic table, its energies are much lower. And we can see that here. The 1s of the hydrogen atom is way up here. The 1s of the fluorine atom is so far below this, you would have to have a much bigger diagram to show the 1s of the fluorine atom, and it's just not being involved in anything at all. But what we see is that the 1s, remember we saw on different sigma interactions, is that the 2py on the fluorine can interact with the 1s, so you have an sp overlap here to form that sigma bond, and that's going to be here and here, and then you've got two other orbitals left. They have nowhere else to bond to. They are going to go across this 1s orbital with part of the negative part of the lobe and part of the positive part of the lobe are both going to be overlapping with the 1s orbital, and so the symmetry does not allow a bond to take place there. And so these come directly across as non-bonding orbitals, and so these form two of the lone pairs that you have on a fluorine atom in an HF molecule. Another example is carbon monoxide, CO. This is quite a complex molecular orbital diagram, and I know some of these labels you don't understand yet. We haven't gone through them. But we have like the 2s on the carbon, the 2s of the oxygen, they combine down here. This is going to be more oxygen character here. The 2 sigma here has some character with from the oxygen 2s, the carbon 2s, and then of course you do get a little bit of overlap from the oxygen's 2p's. The 2pz is going to overlap a little bit because they're fairly close in energy. You do get a little bit here. You get the 1pi's. These are going to be primarily your pi bonds that you have in a carbon monoxide molecule. There's a triple bond there. This would be a lone pair. In here, this carbon 2s contribution is very low, so this is going to represent a lone pair on the carbon. Most likely, this is probably a lone pair on the oxygen. Hard to say exactly what's in there. I would have to do a calculation to see. But you can kind of see here in this diagram where you have on the 1 sigma very heavy on the oxygen here, the 2 sigma heavier on the carbon, and the 3 sigma here, that's a P and S interacting together, much heavier on the S than on the P. Here you have your pi bond interactions. Up here you have your pi stars and your sigma stars up in here as well. So that finishes out lecture 4. A lot of complex information given in these lectures here. So if there's anything that's not making any sense, make sure that you are putting questions in the Panda, or you can send me questions through email, or you can just come on up to my office and we can sit and have a chat. Best of luck, everyone.